This is Pre-Calculus, and this is going to be section 1.3, part 2 of our notes, and we're talking about limits. And here is a formal definition of limit. It's got some applications to calculus. The limit L of a function f as x approaches some constant number c is given by the limit as x approaches c of the function is equal to L. Now, in just about any case, L is going to be a number as well. But there are times when it's possible that the limit does not exist. The reason for that is because the function must approach the same value L from both sides of the function. If that doesn't occur, then the limit will not exist. All right, so we have this notation for you. X with the arrow stands for x approaches some number. So a limit is really talking about what happens when the function gets really close to the x equals c, not exactly what is the function. So there's a difference between what the function equals and what the limit equals. There can be a difference. We will see that in a little bit when we talk about whether or not things are continuous. So conditions for continuity. It follows that in order for a function to be continuous at that same x equals c, it must be true that f of x is defined at x equals c. A counterexample of that would be the function 1 over x at x equals 0. This thing is most certainly not continuous because it's an infinite discontinuity. There's an asymptote at x equals 0. The next step is to verify that the limit as x approaches c of the function does in fact exist. Third, as f of x approaches c from both sides, the limit is equal to f of c. There's some really higher order thinking when it comes to whether or not a function is continuous at a certain point. So we have to do some analysis. Here is an example. Determine if the function is continuous at x equals -3. Use the three conditions for continuity we just talked about. So first, f of x is defined at c. Let's look at f of -3. This is going to be -3 squared plus 3, and that's going to be 12. So check. This thing does in fact have a function that can be evaluated at -3. Part B. Evaluate the limit as x approaches -3 of x squared plus 3. Well, I don't see any asymptotes or getting a 0 on bottom or anything like that. So I'm going to go right ahead and solve this limit by plugging in directly. And that's going to be our number one way to try and evaluate limits. First off, it looks like a straight function, and we're just going to plug it in and see what happens. And I don't run into any problems. I get 12. So the limit is also, in fact, exists. The third condition, then, we have to ask ourselves, is f of negative 3 equal to the limit as x approaches negative 3? Question mark. And that answer is going to be yes, it is. It is true. 12 is equal to 12. So check. We are all good here. The function is continuous at x equals negative 3. Now this particular example is going to be a little bit more complex. We've got a piecewise function, and it says first graph the function, and then determine if it's continuous at x equals 4. Verify using the conditions for continuity. So the top piece, I'm going to plug 4 in here, and I'm going to get 2. So the point 4, 2 is on this graph with an open circle. And then it kind of drifts off to the side. That's our square root function. Next, if x is equal to 4, then I get negative 3. So the point 4, negative 3 is on this graph with a shaded circle. This is the point 4, 2. And the third one, if I take 4 and I plug it in here, I'm going to get negative 4 plus 6, which equals 2. So the point 4, 2 is on here, but also open circle. And then that slope is going to be negative 1. That's my graph. Is the function continuous at this exact point, x equals 4? And that answer is no, it is not, because I see that there's an open circle here. So visually, from the graph, it can be easy to see if a function is continuous or not. This is a removable discontinuity. But let's go ahead and prove it using the conditions. So A, f of 4. That does exist because that would put me in the middle function. Check. B, the limit as x approaches 4 of this function. What is this equal to? Well, remember, a limit is all about what happens when we get really, really close to 4 from both sides. And from both sides, we are approaching this area. And so it looks like it's approaching 2. So the limit is in fact going to be 2. And that exists. So far, so good. However, is it true that f of 4 is equal to limit as x approaches 4? Question mark. That answer is going to be no, because negative 3 is not equal to 2. So no, therefore not continuous. It's very much an analysis question, and to say this is a removable discontinuity because the function exists, but the limit is a different answer. Let's try another. Sketch a graph of the function. Then determine if the function is continuous at x equals negative 1. Verify your results using conditions for continuity. At this point, I would like you to pause the video, see if you can graph the function, and determine whether or not it is continuous at x equals 1. All right, here we go. This function has asymptotes on the x-axis and at x equals 1. But the very first condition, A, f of 1 is undefined. So right away, we can say it's not continuous. Condition A is not satisfied, and this is an infinite discontinuity. There you have it, our formal introduction into limits and continuity. And then please comment on this video in order to earn credit, and then have a nice day.